Welcome to 5.6 the definite integral substitution and area between two curves. So the U substitution that we learned in the last section of 5.5, we're going to extend that into definite integrals. And in order to do that, we're going to have to change the bounds of integration. So, okay. So here, if f prime is continuous on some interval, and excuse me, if g prime is continuous on some interval a, b, some closed interval, and f is continuous on the range of g of u, that is whatever we're plugging into here, then we can rewrite this definite integral right here, where we're going to use u substitution because we have the composition. If we let u equal our g, the derivative of that's on the outside, so we can change this. But when we let u equal g here, well, we're going to have our u inside here. The derivative of u would be g prime. Du would be g prime dx, so we have that substituting there. But the bounds a, b are in terms of x, not in terms of u. So to get them in terms of u, we're going to have to do a little bit of substitution. And you'll see how that works a little bit easier when we actually get into the problems. So I'm going to get to a whiteboard and talk about some things really quickly. Now, the next thing on the notes is this. If we have an even function, so if f is an even function, that is, we can look at this right here. This is some f of x. That means it has symmetry with respect to the y-axis. So there's an equal, it's symmetric on either side of this axis. So if we're taking the integral from negative a to a, we're trying to find the area underneath this curve. That's just going to be twice the area from 0 to a. So this whole area right there would be twice that area. Second piece is if we have an odd function, and this is going to have symmetry with respect to the origin, meaning it's got like a 180-degree rotational symmetry or a double reflective symmetry. If we're trying to find the integral from negative a to a of this, well, because it has a different type of symmetry, this area underneath from negative a to 0 is going to cancel out with this area over here from 0 to a. So that integral from negative a to a is going to get us 0. But really what we want to get at is what is the area between two curves. Now, if we have some function f of x and some other function g of x here, we want to know what's the area between these curves between a and b. Well, the area underneath f would be everything underneath this curve to the x-axis. G, this little piece here is going to take, because we're going to end up subtracting g off to get this. That piece is going to take away from that, giving us this true area that's above there. Now here, this blue area is below the x-axis, so it's negative. So when we subtract off that area, subtracting and negative is really adding to this, giving us that true area. And once again, this is going to be positive. So when we subtract that piece off, it's going to change. Now we don't need to change our bounds of integration, but when we're finding the area between two curves, it's always going to be the top function minus the bottom function on that interval. And that's going to be true for everything. So now, one thing really quickly is this, and I'm going to get back to PDF really quickly, and it's this. Now, this really right here is what I was saying a minute ago. If we're trying to find the area beneath this curve, or between the curves f and g on AB, f would be everything under that. G would be all this blank area. So if we took g away from f, that would give us this true shaded area right here. We can also have functions that are in terms of y. Now, if we're slicing this, like thinking about an approximating rectangle, slicing it vertically, we'd have a little delta x. If we have then this is for y being a function of f. If f is a function of y, as it is over here, and we can have these things that are not specifically functions, but they pass like a horizontal line test, so they're functions in that kind of sense. This right here is, if we're slicing this up, this is a little delta y, because that's a width right here. Now this approximating rectangle is going to be the same as a vertical approximating rectangle, but they're horizontal, so that's a little delta y. Here, if we have top minus bottom, well, it's really the more positive y values minus the less positive or more negative y values, the larger minus the smaller. Same thing's true over here. If we have a function and we're going to integrate it in terms of y here rather than in terms of x, we're going to have the right function minus the left function, and that's kind of like going to be true in general. So we're going to run through these problems really quickly. I'll do a couple. Let's do this really quickly. So, I'll do this on the whiteboard. I don't know if it's better for me to mouse over or do that. I'm just doing it this way today. Okay, so if we're looking at the integral from 0 to 1 of t cubed times 1 plus t to the 4th, that whole thing cubed dt, if we want to just, if we're going to find the indefinite integral, we wouldn't have bounds on this. Finding the definite integrals, we have bounds. So we're going to get a numerical value for this. The other piece is this. Now, we're going to have to make a u. The more complicated function is clearly this parentheses to the 3rd power. And if we look inside here, the derivative of that, well, derivative of constant 0, the derivative of t to the 4th would be 4t cubed. We have a t cubed out here, so we're going to let our u equal 1 plus t to the 4th. Our du is going to equal 4t to the 3rd dt. And really, we have our t to the 3rd dt, so we need to get rid of that 4. So 1/4 du equals t cubed dt. Now, that's going to help us set this up over here. But then we're going to have an integral, and let's just do this kind of in general. We would have this right here is going to be 1/4 du. This right here is our u, so we'd have a u cubed. But notice this 0 and this 1, the bounds of integration are in terms of t. Over here we have an integral in terms of u, so we need to get these in terms of u. So if this is how u is defined, we can almost use like a what's u at 0? Well, because this is in terms of t, we plug that in for t. We have 1 plus 0 to the 4th. That's going to be 1. So our lower bound changes from 0 to 1, and now it's in terms of u and not in terms of t. To find out what 1 is, well, we're going to need to find what u of 1 is. So we're plugging that into this up here, 1 plus 1 to the 4th. 1 to the 4th is 1, that's going to go to 2. So our new bounds of integration are from 1 to 2. So here, if we pull this constant forward, we have 1/4. Integral from 1 to 2, u cubed du. Add 1 and divide by that. So we're going to have when we divide by 4, it's really multiplying by 1/4. So we're going to have 1/16 u to the 4th, evaluated between 1 and 2. Plug in our bounds of integration. I always leave the constant on the outside. So we're going to have 2 to the 4th minus 1 to the 4th. 2 to the 4th, in fact, is 16 minus 1, which is 15. So this is going to be 15 sixteenths. That's that one right here. Now, the next one in the notes works pretty much the same. So I'm just going to jump over there and kind of mouse over it. This right here, if we look at x cubed divided by the square root of x to the 4th plus 9 dx, and we're taking the definite integral from -1 to 1, this thing in the bottom is more complicated. And if you think about this, x to the 4th plus 9, the derivative of x to the 4th is going to be something 4x cubed. We have our x cubed up here, so this is going to be our u. So here we take that out. We have, this is going to be a 4x cubed dx. We don't want that 4 in there, so we have an x cubed dx. So divide by 4, we sort of that. Now, to get the lower bound, this right here is our u. We're going to plug -1 into this function. So our lower bound, -1 to the 4th, is +1 plus 9 gives us 10. So our lower bound is going to be 10. That's what we have. Upper bound, we're going to plug 0 in. Plug 0 to the 4th plus 9 is 9. So this is going to be the integral from 9 to 10. Lower bound, bigger than upper bound. Not a big deal. We can always change our bounds of integration and make this negative, or we can just integrate it directly. But this is our upper bound and this is our lower bound. So you want to think about that. So in the substitution, we substitute our bounds in. This du over 4, the 1/4 comes through. That was that. This is our u, so it'll be du over square root of u. This 1 over the square root of u is u to the -1/2. Add 1 to this, and that's going to be 1/2. If we're dividing by 1/2, that's multiplying by the reciprocal. That's why we're getting this 2 over 1 out there, times that 1/4, which is the constant. That's that. Plug our bounds of integration in, and we're there with that. Now, this next one is pretty much the same thing. You know, we have a u sub. It's a little bit trickier in the sense that we have a tangent squared times a cosine, and like if you look at that directly, it seems kind of non-integrable. If you let u equal cosine the derivative of that sine, that's not here. If you let u equal tangent the derivative, that's going to be a secant squared. That's not a cosine. It's not really helping us. So by writing this tangent as sine squared over cosine squared, which we often do if we have something where you do like a little quick check of u's and the u's aren't there, we're taking the derivative. We write that like that. Well, one of these cosines cancels one of these cosines. And that gives us a sine squared over a cosine. Well, here's the next thing. Sine squared, because sine squared plus cosine squared equals 1, we can manipulate that to solve for sine squared, and we get 1 minus cosine squared. So we still have our cosine from down here. We have our 1 minus cosine. We can split this up. 1 over cosine, we have here, minus cosine squared over cosine gives us a cosine. So we split the integral up right here. Now we're going to integrate these kind of directly. 1 over cosine is a secant. This cosine we can integrate directly. Last time we said the integral of secant is the natural log of the absolute value of secant plus tangent, and I did a little proof. It's still true. Like it's just one of those things you're either gonna have to have it's like a little trick cheat sheet, facts, memory, something like that. Minus the antiderivative of cosine is negative. It's going to be sine. This is the derivative of sine's cosine. So the rest of this kind of follows directly from that. Now, if we so if we find the total area between these two curves right here, y equals x and y equals x squared divided by 4. We want to find the total area under here. We need to have this piece, oh, and x equals 1. We're going to have this as a couple pieces. Like, define the area that's trapped between the curve y equals x, that's that line here, x squared over 4, that's that parabola there, and y equals 1. It's going to give us this little, like, that's a line, that's a line, and that's parabolic. So it's going to give us this little, I don't know, not like weirdly shaped piece of pizza, if you will, or something like that. Well, we're going to break this up into two pieces, because right here, if we want to get this piece of area, it's going to be under y equals x, but we want to shave off this little bit that's under the squared function. Well, we need to know what this piece is, because at this piece, if we're going to find the lined piece of area, that's under 1, the function y equals 1, but we need to take off the parabolic piece. So here, that's the area trap between the line and the parabola. Here, it's the horizontal line and the parabola. So because this is y equals 1, if we plug that in here, when y equals 1, x equals 1. So this first piece, we want to take the integral from 0 to 1 of this top function, x, minus this bottom function, x squared over 4. That's what this piece is representing. So this is like the hashtag pound or checkered piece. Plus, here this goes from 1 to 2. How do we know this goes from 1 to 2? Well, if you plug 1 in for y here, you multiply by 4, take the square root, that's going to give us x equals 2. So we're going to have to start solving for some bounds of integration. But this piece here goes from x equals 1 to x equals 2. Now, once again, this is underneath the line y equals 1. That's where this 1 is coming from, but above that. So we need to subtract off that piece of area. That's where that's coming from. So that's the setup of this. The rest of it's really just adding 1, dividing by that, adding 1, dividing by that. You know, here the antiderivative of 1 is x. Here, add 1, divide by it, plug our bounds of integration in, and directly integrate. Here, this next one we're going to take a look at, and I'll do it on the whiteboard because it's going to be something that's a little bit weird for most students. Okay, so if we're going to find the area between x equals y squared, x minus y squared equals 0, and x plus 2y squared equals 3, really we're going to do this. This is going to be if this function right here we'll do in red, this is going to be x equals y squared, which is going to be a parabola that's opening up to the right. If you remember from comics, if we solve this thing right here, which we'll do in orange, this is going to be x equals 3 minus 2y squared. So if nothing else, like thinking about this graphically, what's going to happen is this. This is a parabola that opens up or open to the right in a positive x direction. Just like if we have y equals x squared, it's a parabola that opens in a positive y direction. This right here is going to be a parabola that's opening down, which down here is to the left, but it's moved to the right 3 units. So essentially, it's going to be like that. So what we're trying to do here is we're trying to find this piece of green area. Like that's what we're doing. And if you think about it in terms of like little approximating rectangles, which I really think is beneficial, we're going to be slicing it like this. That's a little delta y. Okay. Now, because when we do this in terms of x, we're doing top to bottom. Here we're doing right to left. So we want this function, which that is 3 minus 2y squared. This is the bottom function, y squared. If we just think about this, this is going to be the integral of the right function, 3 minus 2y squared, minus this bottom function, y squared. This little delta y turns into a dy when we do the limit of the Riemann sum, if we were going to do it like that. But here the real question is, well, what are our bounds of integration? What is this and what's this? And we want our bounds of integration because everything's in terms of y's. What's that y value? What's that y value? In order to do that, if x equals y squared and x equals 3 minus y squared, we'll just substitute this in for that x right there, and we get y squared equals 3 minus 2y squared. Solving this for y, we're going to add 2y squared to both sides, so 3y squared equals 3. Divide by 3, we get y squared equals 1. Take the square root, we get y equals plus or minus 1. Now, that means that our bounds of integration are moving from -1 to 1. If you know anything about these two functions, and we talked about even and odd functions, this isn't specifically even, but it has a symmetry where the amount of area below the x-axis is the same as the amount of area above the x-axis. So what I'm going to do is just do this. I'm going to double the amount of area between 0 and 1 of this function. So we have 3 minus 2y squared minus y squared dy. So here, through a little bit of distribution, or just really, it's not even distribution, that's a negative y, combining these things up, we're going to have 2 times the integral from 0 to 1 of 3 minus 3y squared dy. Take the antiderivatives, so we have 2. This is going to be a 3x. If we add 1 to this and divide by it, we're just going to have, oops, this is a y, not an x. This, if we add 1 to this and divide by it, we're going to have minus y cubed. Our bounds of integration is from 0 to 1. So again, I always leave the constant out. Plugging our 1 in, 3 times 1 minus 1 cubed, minus plugging our 0 in, 3 times 0 minus 0 cubed. This is going to give us 2 times quantity. Well, 3 times 1 is 3, minus 1. 3 times 1 is 3, minus 1 is 2. 3 times 0 is 0, 0 cubed 0, 0 times 0 is minus 0, 2 times 2. So the amount of area that's trapped underneath this is, in fact, 4. So I know that's a lot of information, but like realistically, the other videos I have for this, especially the first video out, is from the organic chemistry tutor or something like that. He's really good. He does these, changing bounds of integration, these sorts of things with U subs. He also does the area between the curves with nice little like color drawings and stuff. So take a look at that. I'll see you guys in class, and hope you're doing well.